video some more review examples. These would be examples of problems that you might see on a calculator portion. But still, there's a lot of steps you got to know how to do without your calculator. So these first beginning ones we're just solving. So I'm going to use my exponent rules here. And if they have the same base, I can add my exponents. So here I'm going to get 5 to the 2x minus 2. Here I could rewrite 25 as 5 squared. So 2 plus that is going to be x plus 1. So once these match, remember I can set those equal. So in this one, this would totally be a no calculator question as well. It's relatively easy. Okay. Here I'm solving a log equation. Try and get my camera to focus. There we go. So I'm going to bring up this exponent first before I combine and this exponent. So I'm going to get log base 3 of x to the 6th plus natural log of e squared. And actually, you guys might recognize natural log and e are inverses. Those are just going to cancel, which I could have canceled that here or here. It doesn't matter. Which actually, I might just cancel it above because I just get 2 there, and then equals 10. Okay. So actually, maybe I don't need to bring this up, you guys. I'm actually going to leave it just like this. I wanted to bring it up if I was condensing, but if I'm not condensing, I don't need to bring it up because I'm going to be able to subtract the 2. So I get 6 log base 3 of x equals 8. Now divide by 6. So that's kind of why I want to leave that 6 out in front. So I don't need that part. Okay, so now I have log base 3 of x is equal to 4/3. Okay, so now I can apply an exponential of 3 to both sides. So x equals 3 to the 4/3. Okay, we could put that in our calculator here. So 3 raised to the 4/3. Okay, approximately 4.33. Okay, this one, we again want to get the e part by itself, so I'm going to subtract 6. Divide by -3. So I get e to the 7x plus 9 is equal to 4. Now I want to get rid of e, so I'm going to apply the natural log to both sides. So that'll cancel. So I have 7x plus 9 equals natural log of 4. Subtract 9. Okay, and then divide by 7. And this is where it is a calculator problem, but I'm going to put it all in my calculator at one time so that I get the most accurate answer. So I'm going to say natural log of 4 minus 9, and then all divided by 7. Negative 1.09 if I round to the nearest hundredths. Okay, here, sorry, that should not be a plus sign. Let me check really quick what that's supposed to be. Sorry, pause really quick here, you guys. It's good for us to find these typos, so let's see, mod, review notes, and let's see what we got here. Okay, it's supposed to be subtraction. All right, so this guy is subtraction. Okay, so this is where I do want to condense here. So this is an example of where I would want to bring my exponent up before I condense. So this is log base 3 of x to the 4th minus log base 3 of 12 equals 10. This one doesn't simplify nicely, so I'm going to condense log base 3 x to the 4th over 12. So now I can apply an exponential of 3 to both sides. Okay, 3 to the 10th is going to be kind of big. 59,049. multiply both sides by 12. $708,588. Okay, and we can actually take the fourth root, and to show you guys that, it's under math. So if I want the fourth root, I'm going to type 4 first, then hit math. And then there's this x in front of the root, and then I type the number I want, which I'm just going to hit second answer, the answer I just had. So about 29.01. Okay, this is a positive number, so I know when it goes back in, it is still defined. Okay, this example, my bases are different, and I can't rewrite 4 and 6 to have the same base. So I want to pick one of the bases to use, and I can use either one, 4 or 6. So I'm going to do log base 4, and I'm going to do it to both sides. Now, that doesn't help me cancel over here. It does here, but this allows me to bring this exponent down in front. And then log base 4 of 6. Remember that piece right here, I can write as a decimal if I use my change of base formula. So I'm going to do log of 6 divided by log of 4. Oh, let me switch that. There we go. Divided by. Okay, so about 1.29. So I have 2x plus 5 equals 1.29 times x minus 7. So distribute. So I'm going to do 1.29 times 7. So we've got 2x plus 5 equals 1.29x minus 9.03. Okay, I'm going to add 9.03 and subtract 2x. So we get, and add that, what do I get there? 14.03. Okay. Divide by a negative 0.71. So we get negative 19.76. And again, I don't have to check extraneous solutions on exponentials, just on logs because our domain is not all reals. Okay, last couple examples here, you guys, are dealing with exponential growth and decay and talking about half-life. So remember, half-life, we can use our PERT formula. This is going to be the big one. And remember that R is just going to be negative if it's decaying, okay? So we have, this substance has a half-life of 7,370 years. Find the decay constant, that's R. We have a sample of 1,000 atoms. How much is left after 2,000 years? Okay, so remember, I can put in my initial amount, which is 1,000. And I want to know how long does it take to half is left, so that's going to be 500. Okay, E, I don't know R, and the time is the half-life. So it takes that many years till half of it is remaining. So remember, the kind of cool part about dividing by this number here is I'm always going to be left with a half when I am doing the half-life time. So I have 7,370 R. Okay, we're going to take the natural log of both sides. Okay, natural log of E will cancel, so we have natural log of 0.5 equals 7370R. So natural log of 0.5 divided by 7370 equals R. All right, e to the negative 5 means I need to move my decimal left 5 places, so 4 zeros in front of that. So we're going to get R is approximately negative, and it should be negative for decay, 1, 2, 3, 4 zeros, and then 9, 4. Oh, sorry. 4 zeros, not the number 4. So 1, 2, 3, 4 zeros, 9, 4. Okay, so there is my decay constant. Now they want to know how much is left after 20,000 years. So now I'm looking for a new amount. My initial, I'm still going to use that 1,000. This time I know my rate though is negative 0.00094. And then after 20,000. Okay, so now I just plug this into the calculator to get my new amount. Okay, so we have 1,000 times e raised to the negative 0.1234094 times 20,000. $152.59 atoms. And that's how much would be left after we started with 1,000. That's how many would be left after 20,000 years. Okay, we can also use population using this PERT formula as well. So they're asking, according to this equation, that's a model, what was the population in 2001? So this model is for the population since years in 2001. So 2001 was the starting point. So the starting population is right there. So there were 63,467 people in 2001. Is this model a growth model or decay? Well, this is negative, so it's decaying. Decay because R is negative. Okay, find the growth or decay rate. So they want me to solve this. Oh, sorry, that is it. So negative 0.035. So if we move that, this amount, okay, it is decaying 3.5% each year. Okay, all right. According to the model, what will the population be in 2030? So 2030 minus 2001 is 29 years. So that's what I'm going to put in for T. So we have A equals 63,467 negative 0.035 and then times 29. And then this I just put in my calculator. All right, let me do this side. It seems to be easier to see over there. Okay, so we have 63,467 times e raised to the negative 0.035 times 29. All right, so this is population, so I'm going to use a whole number here. So 23000. We'll round that up to a 1. All right, that's our last example, guys. This note just says make sure you know those interest formulas.